Hello everyone, this is Saurabh from Edureka and welcome to this TensorFlow tutorial on deep learning. In this tutorial, we'll be covering all the fundamentals of TensorFlow to implement a use case that is a Nevel Mine Identifier, NMI. So let's begin, guys. Nevel Mine Identifier is a pretty serious problem in which one needs to identify whether an obstacle is a rock or a mine on the basis of sonar signals bounced or reflected by it. So let's get into the details of this use case. Imagine you are hired by the US Navy and your task is to create a model that can differentiate between a rock and a mine. We will call this model as a Naval Mine Identifier, NMI. A naval mine is a self-contained explosive device placed in water to damage or destroy surface ships or submarines. If you want a better picture, just consider the diagram that is there in front of your screen. So here we have 3 submarines, out of which one is broken down into small pieces when it passes through a naval mine. The major use of these underwater mines or naval mines began in World War I. Similarly, in World War II, nearly 700,000 naval mines were laid, accounting for more ships sunk or damaged than any other weapon. So now you must have understood the importance of this use case. This model can actually save a lot of lives. Now let's look at the data set that we'll use to create this deep learning model. Here we'll be using the sonar dataset. This dataset contains sonar signals which includes 111 patterns bounced off a metal cylinder and 97 patterns bounced off a rock, both at various angles and conditions. Hence, every record in the dataset represents a pattern. Now let me show you the dataset. So there are total 61 columns in the dataset, in which the first 60 columns is a set of 60 numbers in the range from 0.0 to 1.0. And the last column of every record is a label which represents the name of the class. That is either a rock or a mine. Let me explain you with an example. If the pattern is defining a rock, then the last column would contain the letter R. Similarly, if the pattern represents a mine, then the last column would contain the letter M. So if you notice in the data set as well, in the last column we have either R or M. So this is nothing but the class to which the pattern belongs to, whether it is a rock or a mine. So this data set contains both the patterns which can be analyzed for prediction and the actual outcomes. That is, whether the pattern represents a rock or a mine. Hence, it can be used for training the TensorFlow model that we want to create. Now is the time to understand the flow to implement the Naval Mine Identifier. Now don't be scared of the fancy terms that I'll use here. You'll understand them all in the coming slides. For now, we'll understand the steps that will be involved in implementing the TensorFlow use case. So we'll begin by processing the data set that we have. We'll define features and labels. We'll divide the data set into 2 parts, training and testing. Then we'll train our model on the training data. We'll try to reduce the error. After that, we'll test our model on the test data and we'll calculate the accuracy. Here, our ultimate goal is to achieve the highest possible accuracy. So guys, let me quickly execute the TensorFlow model that I've already created for you. For that, I'll open my PyCharm. So this is my PyCharm, guys. Over here, I've already written the code in order to execute the use case. So I'll just go ahead and run this. So this is how the output looks like, where the deep learning model is getting trained. If you observe, with every iteration, the accuracy is increasing and the error is decreasing. So we'll stop it right here. So guys, any questions, any doubts with respect to what is our use case and what is the data set about, you can go ahead and ask me. Any questions? Emma has a question. She's asking what is the size of the data set. So the size of the data set is 208 cross 61, which means we have 208 rows and 61 columns, out of which the last column is nothing but the label, or you can say the class represented by that particular pattern. Any other questions, any other doubts, guys? Fine, so we have no questions. So with this, we'll get back to our slides and understand the fundamentals of TensorFlow first before we get into the implementation details of this use case. In order to implement this use case, we'll be using TensorFlow, which is a Python library. In TensorFlow, data is represented in the form of tensors. So let's understand that first. TensorFlow programs use a tensor data structure to represent all data. You can think of a tensor as an n-dimensional array or list. Now consider the example that is there in front of your screen. So the first tensor has dimension 0. The next tensor has 2 dimensions because it has rows as well as columns, and the last tensor has dimension 3 because it has one more field. Now in TensorFlow system, tensors are described by a unit of dimensionality known as rank. So let's understand that. So a rank 2 tensor is what we typically think of as a matrix, and a rank 1 tensor is a vector. Now let us focus on the table that is there in front of your screen. So rank 0 is nothing but a scalar which has magnitude only. you can think of its example as 483, 689, numbers like that. Then when I talk about rank 1, it is a vector which has magnitude and direction both. And you have the example in front of your screen, 1.1, 2.2, 3.3. Similarly, when I talk about rank 2, it is nothing but matrix, tables of numbers, you can say rows and columns. And you have an example here as well. Similarly, when I talk about rank 3, you can see the example here. So this is how we actually define the rank of a tensor. Now let us move forward and understand various tensor data types. You can see in the table that there are multiple data types. There is integer type of 8 bits, 32 bits, etc. Similarly, even for float type. Then there is even string and boolean type. However, in TensorFlow, you don't need to specify the tensor data type. It will automatically assign the correct type. But if you want to save the reserved memory, for example, if you know you require only 32 bits, then there is no point in reserving 64 bits. So at that time, you can specify the tensor data type to be of 32 bits. So that way you can save some memory. So guys, now is the time to understand what is TensorFlow. TensorFlow is an open source software library released in 2015 by Google to make it easier for developers to design, develop, and train deep learning models on neural networks. Now, TensorFlow works by first defining and describing our model in abstract. And then we are ready, we make it a reality in a session. Now, don't worry guys, in the next slide, I'll explain what exactly is session. This description of the model is what is known as your computation graph in TensorFlow. And remember guys, only tensors may be passed between the nodes in a computation graph. Now if you notice, TensorFlow is nothing but the combination of two words, tensor, which we saw in the previous slide, and flow, which is nothing but the tensors flowing through a computation graph. So guys, let us dig a bit deep and understand the TensorFlow code basics. The TensorFlow programs consist of two sections. One is building the computation graph. Here we just describe the computation. It doesn't compute anything, it doesn't hold any values, it just defines the operations specified in your code. When you execute it, the output will just be an abstract tensor. No actual calculations will run, only operations will be created. To actually see the result, we need to run the session. Generally, you build the graph first and then you launch the graph, right? This session allows us to execute the graph or a part of the graph. Let us understand this with an example. So this is how you build a computational graph. Here we have defined two constant nodes. Node 1 has a value of 3 and node 2 has value 4. Then what we do, we need to run it inside a session in order to execute the graph. Now let me go ahead and execute this practically in my PyCharm. This is my PyCharm again guys. First thing I need to do is import TensorFlow as TF. Then we'll define two constant nodes. Node 1 equal to TF dot constant, and the value will be stored inside it will be 3.0. It is of TF dot float 32 bits. Then we'll define one more node and let it be TF dot constant again, and the value that will be stored will be 4.0. Next up, when we try to print these two nodes, let's see what happens. Let's go ahead and execute this. Now the output here is just an abstract tensor. No actual calculations are running, only operations are created. Now to execute this graph, let me tell you how you can do it. First, I'll comment this line. Now to execute this graph, we will run it inside a session, as I've told you earlier as well. So session places the graph operations onto devices such as CPUs or GPUs and provides methods to execute them. So I'll type in here ses is equals to tf dot session. So this will basically launch the graph and create a session object. Next up, we will run the results. So for that, I'm going to type in here print ses.run, and we want the values of node 1 and node 2. So let us go ahead and type that, node 2. Yeah, this is fine now. And when we are finished with the session, we need to close it in order to free up the resources that were used. So that is also very easy. Just type in ses.close. That's all you need to do. Go ahead and execute this. So we have got the output as 3 and 4, which is absolutely correct. These are the values stored in the constant nodes 1 and node 2. There's one more way in order to launch the graph and close the graph apart from the one that I've shown you. So let me show you how you can do that. For that, what I'm going to do, I'm going to first comment this line, even this line. So for that, what I'm going to use the with statement of Python. So for that, I'll type in here with tf.session as ses output equal to ses.run. node 1, comma, node 2. Go ahead and print the output. So if you're not familiar with what this does, basically it will use a session for the block of code following the statement and then automatically close the session when done. The same way it works if you open a file with the with statement. So let us go ahead and execute this and we'll see what happens. So again, we have got the same output 3 and 4. So I've explained you a couple of ways in which you can start and stop a session. So guys, let me explain you this with one more example. For that, I'll open my slides once more. Here I have first defined a constant node A which has a value 5 in it. Then I've defined one more constant node which is B and the value stored in that node is 6. After that I've defined one more node and this is nothing but the multiplication of A and B. So till now we have built our computation graph. Next up we need to run it inside a session. So when we run the session, what will happen? The values that are stored in A and B will be multiplied. So let us see if that happens. Yep. So after running the session, we got the output as 30, which is nothing but the multiplication of A and B. So when you multiply 5 by 6, obviously you will get 30. Now guys, I'll open my PyCharm and execute this practically. Let me remove all of this. So first I'm going to define one constant node. The value that will be there will be 5.0. One more constant node. The value inside that node will be 6.0. Then C is nothing but the multiplication of the two nodes. So we have built a computation graph. Next up we need to create the session object which will launch the graph. So ses is equal to tf dot session. So guys, you can even use a with statement of Python in order to do that. But yeah, I'm comfortable with this, so I'll continue from here. And then what I need to do is just run the session, ses.run C. That's what I want to compute. And yeah, finally just close the session. Ses.close. Go ahead and execute this. So we have got the output as 30, which is nothing but the multiplication of nodes A and B, which stores the value 5 and 6 respectively. Now I know multiplication of two numbers is not a big deal, but it is a good example for understanding how things work in TensorFlow. Now, what if I tell you that you can actually visualize a computation graph? Let me tell you how. For that, I'll open my slides. So for visualizing TensorFlow, we use TensorBoard. TensorBoard is a suite of web applications for understanding your TensorFlow graphs. For that, what we need to do, we need to first create the object of class for writing summaries. One such class is called FileWriter. So it has two arguments. The first argument, we need to just specify the path of the directory where we want the information to be stored. That will be used by TensorBoard in order to build the graph. After that, we need to run this particular command in the command line, and we'll see that TensorBoard will run as a local web app on port 6006. So I'll quickly open my PyCharm and I'll execute this practically. Let me close this. Yeah. So after that, I just need to create an object, FileWriter object, FileWriter equals to tf.summary.FileWriter, and I need to provide a path here. So I've already copied the path. I'll just paste it here. And once you have written the path, just type the name of the file. So I'll just type in here graph. And after that, I need to add ses.graph, which is used for creating a graph object. So just type in here ses.graph. All right. So now if I execute this, I'll see a directory here by the name of graph that will contain the information which will be used by TensorBoard in order to build the graph. Let us see if that happens or not. I'll run the code. And yeah, you can notice here that there's one more directory created that is called graph. Next up, we need to open a command line and execute one command. Let me show you how you can do that. So over here, first I'll move in the PyCharm directory. Yeah. And then I'm going to type in here TensorBoard --log dir equal to the path TensorFlow. Just go ahead and execute this. So it says that TensorBoard runs as a local web app at port 6006. Let us see how our graph looks like now. So this is how our graph looks like. It has two constant nodes here and one node for multiplication. So when I click on each of these nodes, there will be some information displayed about that node. So if you notice here, it is a float type. It also contains the value that is stored inside this particular constant node, which is 5. There are 0 inputs and 0 outputs. Similarly for this constant node as well, it is a float type and it holds the value 6. Similarly, when I click on this particular node, we can see that it is again float type and it has two inputs, const and const underscore 1. So these two inputs will be multiplied and we'll get the output. I have a question popped on my screen. This is from Michelle. She's asking, why aren't we seeing the output here? It says output 0. Alright, fine. So I'll tell you, this is just a computation graph. This explains what are the operations that you have specified in your code. It doesn't execute that. Alright, so this answers your question. Alright, fine. She's happy with the answer. Any other questions, any other doubts, guys? Go ahead and ask me. Anmol, Jasir, Emma, Janice, any questions? Fine, guys. So there are no questions. So I'll go back to my slides once more. And now is the time to understand what are constants, placeholders, and variables. So constant, as the name tells, that it will always produce a constant result. So I'll explain this with an example. So over here we have a couple of constant nodes. First node has value 3, another node has value 4. So when I execute this particular graph, I will always get the values 3 and 4, or you can say the values that are stored inside these two nodes. Now what if I want my graph to accept the external input? Now let me explain that with an example of our use case only. So here we want the features to be fed back to the graph. That we cannot do with the help of constants. For that, what we need placeholders. Now a placeholder is nothing but a promise to provide a value later. Let us understand this with an example. So over here we have a couple of placeholders A and B of float 32 bits. And notice that we have initialized no values. Then we have one more tensor adder underscore node, which is nothing but the addition of two placeholders. Then we have first launched the session, and when we are running the session, we feed in the values of the two placeholders, as you can see here. So the value that will be fed back to the placeholder A is 1, 3. The value that will be fed back to the placeholder B will be 2, 4. Now let me execute this practically in my PyCharm. Let me remove all of this. All right. So I'll define a placeholder A, tf dot placeholder, which is of float 32 bits. Similarly, B will be again a placeholder of tf dot float 32 bits. Then we define one more node, adder underscore node, which is nothing but the addition of these two placeholders. Next up, we need to launch the graph. For that, I'll type here ses is equals to tf dot session. And next up, we need to run the graph. Print ses dot run and adder underscore node. And we need to feed the values of A and B as well. So for that, I'll type in A 1, 3, B 2, 4. Now let us go ahead and execute this and see what happens. So here if you notice, I get the output as the sum of the two placeholders A and B. So the first value 1 will be assigned to the placeholder A and value 2 will be assigned to the placeholder B. So their sum will be 3. Similarly, A will be assigned to the value 3 and B will be assigned with value 4. Hence their sum will become 7. Now let's get back to our slides once more. Now the question here is how to modify the graph if I want new output for the same input. I mean, if I want my model to become trainable, I need some parameters that can change after every iteration so that the model output can be as close as possible to the actual output. For that, we need variables. Now variables, as the name explains, the value of the variable will keep on changing. When you train a model, you use variables to hold and update parameters. Variables are in-memory buffers containing tensors. And remember, they must be explicitly initialized, unlike constants and placeholders. So let me explain you the code that is there in front of your screen. So here we have two variables, W and B, and I've initialized both of these variables with value 0.3 and minus 0.3. So if I train my model, the values of these two variables should change in order to reduce the output. Don't worry, you'll actually understand that when I explain you the loss function and optimizers. There you'll understand how we actually train our model and how actually variables are updated after every iteration. And in order to initialize the variables, we use tf.global underscore variables underscore initializer. This will add an operation to initialize the variables. Then we run ses.run init. This will run that operation. And remember, we only run it after launching the model. For now, let us go ahead and execute our first model. So this is our first model, guys. Over here we have imported the TensorFlow as TF. Then we have defined a couple of variables W and B, and we have initialized them with 0.3 and minus 0.3 values respectively. Then we have a placeholder X. After that we have defined one linear underscore model, which is nothing but W into X plus B. Then we have initialized the variable, launched the graph, and then we are running the session. And during that, we are running the session and feeding the values of x. So this is basically what our model is. But we don't know how good it is yet. So obviously we cannot increase the efficiency without knowing the error. Let's understand the general flow of how we increase the efficiency. So first we create the model as you have seen in the previous slide. Then we calculate the loss. Loss is basically how far our model's output is from the actual output. Then we try to reduce the loss by updating the variables. Then again we check the loss and update the variables, and this process keeps on repeating until the loss becomes minimum. And now is the time to understand how we calculate loss. So in order to find out the loss, we should first define a placeholder, and we have named it as y, which will hold the desired output, or you can say the output that we already know. Then we will find the difference between the linear underscore model or the output of our model with that of the output that we already know, the placeholder y. Or you can say the difference between the model output and the actual output. Then we find the square of that particular difference, and then finally we sum all the squared errors that we have calculated in the above line. So we'll sum all of these squared differences. Then what we have done, we will run the session, calculate the loss, and we'll feed in the values of x and y. So I'll execute this practically. For that, I'll open my PyCharm. Let me remove all of this. So yeah, first we'll define a variable tf.variable with the initial value as 0.3, and it is tf.flow 32 bits. Then we will define one more variable tf.variable minus 0.3 comma tf.float 32 bits. Then we'll define a placeholder that we will use in order to provide the inputs or to feed in the inputs. So let me throw in a comment here, inputs and outputs. And I can throw in one more comment here that says model parameters. Alrighty then. So now we'll define a placeholder x, which will actually hold the input values tf.placeholder. It will be of float type 32 bits. Then we'll define one more placeholder y, which will actually hold the actual output of the model, which we already know. Placeholder tf.float 32 bits. Alright. And just between that, we'll define one more node, linear underscore model, which will give the output of this particular model, which we don't know. So that's the difference, guys. This y is a placeholder, and the values to this y will feed in when we are running the session. So that will be the actual output of the model. And this will be the output of the model, which will come after executing the model. So this will be nothing but w into x plus b. Fine. And now we are going to define the loss function. So I'll type in here squared underscore delta is equals to tf dot square linear underscore model minus y, which is nothing but the model output and the output that we already know. So linear underscore model is the output that we'll get through our model, and y is a placeholder which will have the output values that we will feed it. Then we're going to define a loss function. So loss is equals to tf dot reduce underscore sum of all the squared delta. So we have defined a loss function here. Next up, what we need to do is initialize all the variables. For that, I'm going to type in here init is equals to tf dot global underscore variables underscore initializer. So this global variable initializer will add an operation to initialize a variable. Now we need to launch the graph. For that, we need to create a session object, and we know how to do it. Ses is equals to tf dot session. Yeah. And now we are going to write in here ses dot run init. So this will run the operation that we have defined when we were talking about global variable initializer. And after this, our variables are initialized. So now what we need to do is just run the session. Ses dot run, calculate the loss, feed in the values of x. So let it be 1, 2, 3, 4. And now the placeholder y, feed in the value of placeholder y. So we'll keep it as 0, minus 1, minus 2, minus 3. Now let us go ahead and see how much is the loss. So the loss that we have calculated is 23.66. Let me just close this once. Now over here, if you notice, if I change the value of W and B, I can actually reduce my loss. Let me show you how I can do that. I'll take a pen. So instead of 0.3 and minus 0.3, if my W becomes minus 1 and my B becomes 1, then linear underscore model will become equal to Y. That means the output of our model will actually become equal to the actual output, the output that we know. So let me tell you how it will happen. So our linear underscore model is W into X plus B. So we'll take the values of X one by one. So the first value of X is 1. So let me take that first. And the value of B is minus 1. So minus 1 into 1 plus 1 is equal to 0. So the value of our linear underscore model is 0. And over here also the value of Y, that is our placeholder or the actual output, is also 0. Let us take the next value of X, which is nothing but 2. 1 minus 1 into 2 plus 1 is equal to what? Minus 1, which is again equal to Y. Similarly, minus 1 into 3 plus 1 is equal to minus 2, which is also equal to our placeholder Y. Finally, if I take the last value of X, which is 4 plus 1, it will be equal to minus 3. So this is how, when we update the variables, we can actually reduce the loss. So here, if I keep the values of W and B as minus 1 and 1 respectively, the loss that I'll get will be 0. So this is how you can actually reduce the loss, by updating the variables. So when I was explaining variables, where I told you that in order to make the model trainable, we need to update the values of variables. So this is what I was talking about. So by changing the value of variables, we can actually reduce the loss. We can make the model output as close as possible to the actual output. Now, if I make this as minus 1.0 and this as 1.0, we should get 0 error. Let us see if that happens or not. So we have 0 loss. But over here, I have manually done it. I have manually updated the variables W and B. What if I want my model to do it on its own? What if I want the machine to learn the new values of W and B? That will minimize the loss. So at that time, we need optimizers. So for that, I'll open my slides once more. Let me remove all of this. Yeah, and keep this to its normal value, 0.3. It was plus 0.3, yeah, and this will be minus 0.3. Now I'll open my slides. So in order to increase the efficiency and minimize the loss and update the variables, we use optimizers. These optimizers modifies each variable according to the magnitude of the derivative of loss with respect to that variable. Now what does that mean? It means basically that an optimizer will check the magnitude of the derivative of loss. That means an optimizer will check the change in the loss with respect to the change in the variable. And if the loss is decreasing, then it will keep on changing the variable in that particular direction. I hope I'm clear, guys. If you have any questions or doubts, you can ask me right now. It is a very important concept. All right, Jason wants me to repeat it. Fine, Jason, I'll do that. So an optimizer will actually calculate the change in the loss with respect to the change in the variable. And if the loss is decreasing, then it will keep on updating the variable in that particular direction, so that loss becomes less. So I hope you have understood it, Jason, now. Yeah. So here we'll use gradient descent optimizer. Let us understand this with an analogy. Suppose you are at the top of the mountain and your task is to reach the lake, which is present near the valley. And the catch here is that you are blindfolded. So how will you approach this task? One way of doing this is to observe the ground near you and move in the direction where the land tends to descend. Consider every step that you take as learning rate and the position as weight. The whole process is called as loss function. When you reach the lake, consider that point as global loss minimum. Now you can apply the same concept on our model as well. Where the ground tends to descend, similarly the optimizer checks in which direction should the variables be updated so as to decrease the loss, and will keep on updating the variables in that particular direction. So let's understand the math behind gradient descent optimizer. First, we calculate the loss. How we do that? By summing all the square differences between the model output and the actual output, and then dividing it by 2. So here our target output is nothing but the output that we know, and output is nothing but the model output. After that, we calculate the change in the variable delta W. This is equal to the learning rate multiplied by the rate of change of loss with respect to that variable. After that, the new variable or the updated variable is equal to the sum of the change in the variable plus the old value of that particular variable. So it will be W plus delta W. Now let me simplify this equation for you. So over here, when we are calculating delta Wj, which is equal to minus of learning rate into delta J by delta Wj, or you can say the rate of change of error with respect to that particular variable, we put in the values of J, then we find out the derivative and we get the equation as learning rate into summation of target I minus output I, that means the actual output minus the model output, into xj of I, which is nothing but your input. So guys, any questions, any doubts till here? Any questions related to what are optimizers and how does the gradient descent optimizer work? Any questions, you can go ahead and ask me. Alright, so Dave wants me to repeat it. Fine, Dave, I'll do that. So the first thing that you do is first you calculate the error. What do? You find out the difference between the actual output and the model output. Then the difference is squared and you sum all of those squared differences and then divide it by 2. This is how you calculate the error. Then what you need to do is you need to update the variable so as to reduce the loss or the error. So how you do that? You first find the change in the variable, which is equal to minus of learning rate multiplied by the rate of change of loss with respect to that variable, del j by del wj. So after that, what you do, you calculate the new updated variable, which is nothing but the old variable plus the change in that variable, which is nothing but the old variable plus the change in that variable, delta w. That's how it works. So we have got a new value of the variable. So again, the model will check how much is the loss, and again the whole process will repeat. Again, we'll update the variables. Again, it will check the loss, update the variables until and unless the loss becomes a minimum. All right, he's happy with the answer. Fine guys, so we'll move forward and see how we can apply gradient descent in our model. Now in order to modify the variables in our model, we'll use the code that is there in front of your screen. Here we will first create an object of class tf.train.gradient-descent-optimizer, and it will implement the gradient descent algorithm. It takes one argument as the learning rate. The second part, this minimize, returns an operation that applies gradients. It will reduce the loss by updating the variables. Finally, just run the session and feed in the values of x and y, and then evaluate the variables w and b. So let me go to my PyCharm and execute this. Let me comment this line first. So after defining loss, we will optimize our model. We'll write in here optimizer equal to tf.train.gradient descent optimizer with a learning rate of 0.01. Learning rate is nothing but the steps in which you change your variable. Then what we do, we will write in here train is equal to optimizer.minimize loss. Alright. No doubts till here guys. If you have any questions, write it down in your chat box. Fine, so there are no doubts. And after initializing the variable, we need to run the session. So for that I will use a for loop. So I'll type in here for I in range 1000 ses.run train, comma, feed in the values of x and y. So I'll just copy it from here and I'll paste it there. Alright. Then go ahead and evaluate the variables w and b. So we have got the new value of w as minus 0.99999969 and the new value of b as 0.999999082. Now if you can recall, when we were calculating it manually, we got the output for w as -1 and for b we got it as +1. And these two values are almost the same. So minus 0.9999 can be rounded off to -1 and 0.9999082 can be rounded off to +1. So this is how you actually build a model, then you calculate the loss, and then you train the model. I hope I'm clear. If you have any questions, any doubts, go ahead and ask me. No questions? Fine. So I'll go back to my slides. So guys, this brings us to the most awaited topic of today's session, which is the implementation of NMI, that is our use case, which is Neville Mine Identifier. So guys, let me first tell you the steps that are involved in order to implement this use case. First, we need to process the data set that we have. We'll first read the data set. Then we are going to define the features and labels. So what are labels? Labels are nothing but the class to which the pattern represents. In our case, it can be a rock or a mine. Then we need to encode the dependent variable. And here the dependent variable is nothing but your label. So we are going to encode those dependent variables. After that, we are going to divide the data set into two parts, one for training, another for testing. And by the end of this step, our data set is now ready. Next, we are going to use TensorFlow data structures for holding features, labels, etc. So here we'll be defining weights, biases, we'll have a couple of placeholders for inputs as well as for the desired output that we already know, and we'll also define one tensor that will be our model output. Then we are going to implement the model. We are going to write the logic in order to implement the model. Then what we are going to do, we are going to train the model on the training data that we have. So in this particular step, we have divided the data set into two parts, training and testing. We'll use that training data to train our model. Then we are going to calculate the error. That is how far your model output is from the actual output. And then we'll try to reduce this error. And when we reach to a point where the error becomes minimum, we are going to test our model on the test data. Or you can say we are going to make prediction on the test data. And that will give us the accuracy of our model. So this is how we are going to implement the use case. Now I'll open my PyCharm and execute this practically, guys. So guys, we'll first start with importing the necessary libraries. First, we'll import matplotlib, which is used for visualization, then TensorFlow, the NumPy, Pandas, and sklearn as well. So these are the libraries that we are going to use. So we need to import these libraries. Then we are going to read the data set. For that, we are going to use Pandas. So we're going to convert this data set into a data frame, a Pandas data frame, and we are going to give the path to where our file is stored or our data set is stored. Then we are going to define features and labels. So here, X will be our feature. So basically the first column till the 60th column will be our features, and the last column represents the label, as I've told you earlier as well. So the last column will be a label and it will be stored in Y. After that, we need to encode the dependent variable, which is nothing but our label. Now we'll perform label encoding first, and then we're going to perform one-hot encoding. So guys, I'll explain you one-hot encoding and label encoding with a pen. So suppose if I have labels like rock, then mine, then again rock, then one more mine. First we'll perform label encoding, in which I'll assign values to it. So suppose if I assign 0 to a rock and 1 to a mine, so I'll keep it that way for the rest of the rows as well. Alright, so now we'll perform one-hot encoding, in which we'll have two columns, one for mine and another for rock. So wherever the data represents a mine, it will be 1. So this basically represents a rock, so it will be 0. This row represents a mine, so it will be 1. This represents a rock, so it will be 0. Similarly, this represents a mine, so it will be 1. Now the second column, wherever the data represents a rock, we'll keep it as 1. So this represents a rock, we'll keep it as 1. This represents a mine, so let it be 0. This will again be 1 because it represents a rock. This represents a mine, so we'll keep it as 0. So this is how you perform one-hot encoding. So what is one-hot encoding? Basically, only one input will be active at one time. So basically, what is one-hot encoding? Only one input will be active. So let us move forward now. So this is the function that actually defines one-hot encoding. So this is where we have performed the one-hot encoding. Then what we are going to do, we are going to read the data set. So X is basically your feature and Y is one-hot encoded label. Then we're going to shuffle the data set. We need to shuffle the data set because the whole data set that we have, it is present in an order. For example, in the beginning we have mines and then we have rocks. So we need to shuffle it. So after doing that, we're going to split the data set into two parts, training and testing. How we're going to do that, you can see it over here. So we have defined the test size as 0.20, which means the 20% of the data set will be your testing data set. Now if you can go ahead and inspect the shape of the training and the testing data, although it's not necessary, but still if you want to go ahead and do it, you can do that as well. Then we are going to define the important parameters and variables to work with tensors. So first we are going to define learning rate. So we have seen what exactly learning rate is. Then we're going to define the epoch. Epoch basically means the total number of iterations that will be done in order to minimize the error. Then we're going to define a loss function, cost history. Then we have n_dim. So what is ndim? So basically ndim is nothing but the shape of your features which is stored in X. And that too, it will only include the columns, the number of columns. So then we'll print it, and you can still avoid this step if you don't want to print it, it's all fine. Then you define the number of classes. So since we have only two classes, that is mine and rock, we're going to keep it as 2. Then we're going to provide the model path, which will be nothing but the place where we want to store our model. So I've given the same path in which I'm currently working. So you will see a couple of files created when we execute this model. Then we need to define the number of hidden layers, the number of neurons for each layer. So basically I've talked about hidden layers, neurons, multi-layer perceptron, everything in detail in the previous tutorial. So you can go through that if you have any doubts. Then we have the number of neurons for hidden layer 1, 2, 3 and 4. So we're going to take 4 hidden layers. So this is nothing but an example of multi-layer perceptron. So X is our placeholder in which we're going to feed in the input values, or you can say the data set. It is of float 32 bits. And then the shape of this particular tensor is none comma ndim. So ndim is what we have seen earlier. So if I write here none, which means it can be any value. Then we'll define a variable w, which will be initialized with zeros, and it will have shape n underscore dim, which we know what it is, and n underscore class, which is nothing but the class to which a pattern represents. So we have two classes here, so it'll be n underscore dim comma 2. Then we have one more variable b, we'll fill it with zeros, or we'll initialize it with zeros, and it'll have a shape of n underscore class, that is 2. Then we're going to define a placeholder y dash, which will be nothing but the output of our model that we already know. And its shape will be none comma n underscore class. None can be any value, and we know n underscore class is equal to 2 because we have only two classes, mine and a raw. So now we are going to define a model. We're going to name it as multi-layer perceptron because it is an example of multi-layer perceptron. So first we'll define the first hidden layer in which it will be nothing but the matrix multiplication of your input and the weight, and then we're going to add it to the bias. Then we're going to pass it through a sigmoid activation function. Then the second hidden layer also the same thing will happen, and the input for the second hidden layer will be the output of the first hidden layer. So we're going to type in here layer underscore 1, and then we're going to define the weight, which will be h2. So matrix multiplication of that and then add it to the bias. Similarly for hidden layer 3 as well. And in hidden layer 4, instead of using sigmoid activation function, we'll use ReLU activation function. And then finally comes the output layer in which we're going to perform matrix multiplication, output of the previous hidden layer and the weights, and then we're going to add biases to it. So now we need to define weights and biases for each layer. So H1 is the weight for the first hidden layer. So we're going to define that. It'll be a variable, and it'll be a truncated normal of n underscore dim and n underscore hidden underscore 1, which is nothing but the shape of this particular tensor or this particular variable. N underscore dim we know, and n underscore hidden underscore 1 is nothing but 60. Similarly for other weights as well. And the same goes for biases as well. Here we'll have shape which is equal to n underscore hidden underscore 1, hidden underscore 2, 3 and 4. And then finally the output bias will be equal to n underscore class, which will be nothing but 2 because we have only two classes. Then we need to initialize all the variable, which we have seen how to do that. After that we're going to create a saver object in order to save our model. Then we're going to call the model that we have defined above. Then we're going to define the cost function and optimizer. Cost function is nothing but the loss function. So this is a loss function that we have defined here. So over here, if you notice, let me just show it to you. Yeah. So this is how we have defined a cost function. So we're going to use a softmax cross entropy, and logits y is nothing but your output, and labels y dash is nothing but your actual output, or you can say the output that we already know, and this is the model output. Then we're going to perform optimization. We're going to use gradient descent optimizer, and then will be the learning rate will be 0.03, which we have defined above, and then it will be minimizing the cost function or the loss. So this is how we'll optimize it. Then what we need to do, we need to create a session object that will launch the graph, and this will initialize all the variables. Then we need to calculate the cost and the accuracy for each epoch. How are we going to do that? We're going to use for loop for that. So first we'll define MSE underscore history and accurate history. We'll keep it empty. Then we're going to define for epoch in range training underscore epochs. Over here, first we'll run the training step. We're going to feed in the values of train underscore X and train underscore Y, which is nothing but the training data. Then we're going to run the cost function, or you can say the loss. And again, feed in the values of train underscore X and train underscore Y. Then what we're going to do, we're going to define cost history, which will be append the cost history comma cost. So whatever cost history we have, whatever cost we'll get it here, it will be appended and it will be here cost history. So we can see that for every epoch. That's why we are doing it. So it will be appending one by one. Then we're going to find out the correct prediction, which will be equal to tf.argmax y comma 1 and argmax y dash comma 1, which is nothing but the difference between the actual output and the model output. And after that, we're going to calculate the accuracy here. And then what we need to do, we'll define a parameter pred underscore y, which will be nothing but sys.run and the actual output, and feed in the test data in order to see how accurate our model is. Similarly, we're going to define MSE, mean squared error, which will be nothing but the difference between the predicted value and the test value. Then we're going to launch the graph here, and we're going to find the MSE history.append. So this will actually keep on updating the MSE value for every epoch. Then we're going to find out the accuracy of the training data. So basically we'll be finding here the accuracy on the training data, not on the test data. And we'll keep on appending so that for every epoch we can see that. Then we're going to print that value for every epoch. After that, we're going to define one more parameter, save underscore path, which will be saver.save ses comma model. So this will actually save the model in the model path. So now we're going to plot the graph of MSE and accuracy. MSE is nothing but the mean squared error, and accuracy will be there on your test data. And mean squared error, we know what it is. So we have calculated MSE here, if you can notice. Then what we need to do, we need to print the final accuracy. For that, we'll first find out the correct predictions made by our model. And then we're going to find out the accuracy. And finally, we're going to print it by running the session and feeding in the values of test data in X and Y. Finally, we need to print in the final mean squared error, which will be nothing but pred underscore Y. Ses.run Y comma feed dict. So Y is our actual output. And feed underscore dict is just we're feeding the test input. Then we're going to calculate MSE, mean squared error, which is nothing but the difference between the predicted value and the actual value which is there in the test data, and then just go ahead and print this. So we'll now start training our model. So let us go ahead and run this. So in the beginning, if you notice, it has printed the shape, and then it is printing the test and the training data shape as well. And now it has started training our model. So you can notice the training accuracy that we are getting here. So it'll keep on repeating this process for 1,000 times, for 1,000 epochs basically. So 1,000 iterations. After that, our model will be trained. So guys, this is the accuracy that we have got on our test data. So this y-axis represents the accuracy and the x-axis represents the number of epochs. So we have 1,000 epochs here. That means it's going to train it 1,000 times. So let me just close it now. And yeah, so we have got the test accuracy as 85%, and the average mean squared error is 24.4505. And our model is saved in this particular directory, which is my current working directory, guys. Now let me close this and open the project structure, and you can see a couple of files that have been created here. So guys, we have successfully trained our model and we have saved it as well. Now what we are going to do, we are going to restore this model. So basically we'll be providing some input to this particular model and it will predict the outcome for us. So it will predict whether it is a rock or a mine. So the whole code remains the same. It's just that you need to provide the model path, which you have done when you were actually defining the model and training it. And then what you need to do is you need to again create one saver object, and after that finally you need to call this restore function in order to restore the model that we have. Over here you're going to provide two arguments. One is ses and another is nothing but your model underscore path, which we have given in the previous step. So guys, this is how it is, and we're going to provide the input from the data set only, which will be from row 93 till 101, but it won't include the 101th row. It will only be there till 100th row. Fine guys, so let us go ahead and run this. So guys, this is how the predicted values looks like. Over here, the original class was R. We predicted a value is 1, which means we have correctly predicted this particular class, and we have got the accuracy as 100%. Similarly, for other values as well. But if you notice over here, we have got the accuracy as 0 because we have predicted the wrong value of the class. Similarly, here as well, it is a mine, but we have predicted it as a rock. So that's why we have got accuracy as 0. So guys, this is how we actually train a model and we restore it. So this is all about Neville Mine Identifier. Now let me give you a brief summary of what all things we have discussed till now. So guys, first we started by understanding what is our use case. We saw what exactly we are executing. We saw what the data set looks like. So the name of our model was Neville Mine Identifier. After that, we understood what exactly are tensors and what is TensorFlow. Then we went through code basics of TensorFlow. We understood various data structures like variables, placeholders, constants, and then we implemented the model using TensorFlow. So guys, any questions, any doubts till now, you can go ahead and ask me. Any questions? All right, Dave says amazing session. Thank you, Dave, for those kind words. So we have no questions. So this video will be uploaded into your LMS. You can go through it. If you have any questions or doubts, you can bring it in the next class. We also have a 24/7 support team that can help you anytime you want. Thank you and have a great day, guys.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!